Welcome. Today we will delve into the depths of secret strategies and engineering marvels of World War II, to the mystery of Operation Pluto, a project that could have changed the course of history. In the months leading up to the Normandy landings, many high-ranking commanders, including Erwin Rommel, dismissed the possibility of a large-scale Allied invasion in Europe as unrealistic. But suddenly, Soviet intelligence reported a massive operation requiring hundreds of thousands of soldiers and unique amphibious vessels. And at that moment, the idea of laying underwater oil pipelines across the English Channel emerged, which seemed impossible. Why did the Allies take such a risk, and how much trust did they have in its success? At the same time, doubts arose within their own ranks. Could engineers create reliable pipelines under enemy noses? And was it worth risking such an ambitious project at all? The stakes were not just about supplying fuel to the front, but about securing a strategic advantage that could determine the outcome of the entire war. In this investigation, we will reveal who was truly behind Operation Pluto and show how this daring engineering venture could have altered the fate of the world. Are you ready to see what is hidden in archives and secret laboratories? Then let's begin. In the dark silence of late night, when only the faint glow of a lamp illuminated his face, the commander of German forces in Western Europe, General Erwin Rommel, contemplatively examined maps and intelligence reports. Doubt was reflected in his eyes, the weight of long-standing uncertainties weighing heavily on his heart. Before him lay reports from various sources, woven into a chain of facts intended to help understand what awaited Germany in the coming months. But even among these carefully gathered data, contradictions sounded, like a whisper, quiet but persistent, reminding him of the uncertainty, of the impossibility of predicting the exact course of future events. The months before the Allied landings in Normandy were a time when most German commanders dismissed the possibility of a large-scale operation on the Western Front as unrealistic. To them, it seemed like a fantasy, too ambitious and risky an endeavor. Despite his reputation as a brilliant strategist, Erwin Rommel also experienced internal resistance. He understood. The Germans had already fortified their positions, creating a powerful Atlantic wall, which in their view should have been an insurmountable obstacle. This front was a chain of fortified points connected by artillery batteries, minefields, and well-trained troops ready to meet any enemy. Its foundation was the belief in the impenetrability of this line. All evidence pointed to the fact that breaking through it was virtually impossible. But it was precisely during these months that Allied intelligence began providing new, alarming information. Soviet sources, having access to German intelligence data, indicated the scale of the upcoming operation. They reported enormous resources that the Allies planned to mobilize for the landing. Millions of people, hundreds of thousands of crews, thousands of ships, hundreds of amphibious vessels. All of this seemed impossible, like a dream that could never come true. Yet, these estimates became the actual basis for planning. Despite obvious difficulties, the Allies were not intending to undertake a small raid or a localized operation. They envisioned a large-scale, risky enterprise, landing massive forces to change the course of the war. It was then that an idea emerged that seemed fantastic: the Operation Pluto project, or undersea pipelines under the English Channel. Within the Allied command structures, a bold thought arose: to create a network of underwater pipelines capable of transporting fuel directly to the shores of France, bypassing vulnerable convoy points and transport ships. Essentially, this idea represented a technological challenge, an incredibly risky and complex project requiring cutting-edge engineering solutions. Building undersea pipelines was not only technically difficult, but also extremely risky. Any failure could mean the loss of the entire supply strategy, and thus the entire operation. Doubts arose within British and American command structures about the feasibility of this project. Evidence indicated that the timeline seemed unrealistic, and the risk of failure was colossal. However, The possibility of ensuring continuous fuel supply, a key resource for engines, armored vehicles, and aircraft, could be the decisive factor in the success of the entire operation. In a situation where every minute could be critical, the ability to deliver fuel without interruption could guarantee battlefield superiority. And it was this idea, despite all doubts and difficulties, that became one of the pillars of the planning process. Deeper questions also arose within the Allied command structures. How secret was this innovation? Could they keep it hidden so that the enemy wouldn't learn about it in advance? Evidence suggested that creating such pipelines would require not only engineering solutions, but also a high level of secrecy. The risk of information leaks and the possibility of the project being uncovered became increasingly apparent. It was hard to believe that, amidst preparations for a large-scale landing operation, the team could simultaneously implement such a complex and secret project. But it was precisely in these doubts that their strength lay, because faith in success, in the impossible, often became the driving force behind great deeds. And here, at the very center of all this chaos and uncertainty, arises the main question. Could the Allies carry out such a large-scale, risky project as the undersea pipelines? How strategically important was this idea? And could it truly become the missing link that would determine the outcome of the entire operation? Part 3 of 14. In a situation where every minute could be fatal, the ability to carry out Operation Pluto could be a decisive factor in the outcome of the entire campaign. Was it justified? Was it worth risking so much for an idea that seemed capable of either salvation or destruction? These questions haunted all the leaders, command, and reconnaissance units. Time was passing, and each day brought closer the moment when this complex network of Allied efforts, from planning to execution, had to demonstrate its strength or remain inactive. In a context where every minute could be critical, the ability to implement Operation Pluto could be a decisive element in the outcome of the entire operation. And this was the internal struggle they faced, between possibility and impossibility, between danger and hope, between knowledge and faith in success. During the darkest hours of World War II, when the fate of the world hung in the balance, fierce battles raged on the fronts, and strategic decisions were made under constant threat, an idea emerged that could change the course of the war. This idea, to lay underwater oil pipelines across the English Channel, seemed incredible, almost fantastical. But within this concept lay the potential to provide the Allies with a stable supply of oil, essential for maintaining the war machine. Deep within British military headquarters, in rooms illuminated by the dim glow of wall lamps, a concept was born that would later be called Operation Pluto, an operation that changed perceptions of engineering possibilities and human determination in the face of unprecedented difficulties. At a time when the global conflict was reaching its peak, technology was not yet prepared for such large-scale tasks. Undersea cables used during wartime for communication were short. Their length and technical capabilities limited their application. The idea of laying long pipelines under the seabed seemed fantastical. Strong currents, tides, constant storms, and the danger of detection made it nearly impossible. In those moments, when everything seemed against them and every attempt appeared hopeless, genius was born. And in 1942, British Admiral, prominent strategist, and far-sighted man, Vice Admiral Lord Louis Mountbatten, proposed this risky but vital project. He sat at his desk, surrounded by blueprints, maps, and reports. The scent of coffee filled the air, and outside, the waves crashed, as if reminding everyone that everything was happening on the edge of possibility and impossibility. His eyes reflected determination, for he understood, if this plan succeeded, it would not only ensure supplies, but also provide a strategic advantage that could be decisive in the battle for control over Europe. The reality of that time dictated harsh conditions. Time was worth its weight in gold, and each day of waiting could be fatal. Therefore, a bold decision was made to carry out the entire installation overnight to eliminate the risk of detection by the enemy or destruction. This required not only engineering brilliance but also absolute coordination, precise planning, and exceptional endurance. However, before beginning the implementation, many questions arose. How to create a pipeline that could withstand pressure, strong currents, and tides? What materials would be suitable for its construction? And most importantly, how to ensure its reliability and secrecy? Initially, standard solutions were considered, using ordinary oil tankers and barrels, temporary reservoirs that could be quickly installed and dismantled. But it soon became clear that such methods were too risky and too vulnerable. In wartime, any leak or failure could cost thousands of lives and jeopardize the entire operation. It was in this context that the idea emerged to create a rigid pipeline capable of withstanding internal pressure and being laid on the seabed. This complex engineering challenge required the development of new materials, new welding technologies, and new laying methods. Drawings, prototypes, and calculations began to appear within the command headquarters. Engineers worked day and night, sparing no effort to bring the project to the implementation stage. During this process, the code Operation Pluto was introduced, symbolizing not only its ambitious nature, but also its innovative spirit. This abbreviated term became a byword for an entire generation of engineers and military personnel who believed that the impossible was achievable. Despite all the difficulties and doubts, the project received approval from the British military leadership. The first steps were taken: material testing, technology verification, preparation for laying. Excitement was felt in every movement, because success would mean not only a technical achievement, but also a strategic victory. The team faced the question: could engineers overcome all obstacles, ensure the reliability and secrecy of such a grand enterprise? Time was against them. Dangers lurked at every turn, and the enemy could discover their plans at any moment and sabotage the operation. Nevertheless, determination and belief in victory prevailed. On the night when the most complex and risky operation was to begin, the entire team gathered on the shore. The silence of the night was broken only by the sound of the surf and the quiet rustling of equipment. Each person felt that they were doing something greater than simply laying a pipeline. They were building a bridge between the possible and the impossible, between hope and despair. It was not only an engineering test, but also a psychological battle with oneself, with fate, and with war. The success of this risky endeavor could be decisive for the entire military campaign on the Western Front. Failure would mean loss of time, resources, and possibly victory for the enemy. But victory was not only a technical achievement. This is proof that a person unafraid of difficulties is capable of overcoming even the most seemingly insurmountable obstacles. This is the essence of the entire project, its value, and its dramatic core. The thorny path to the realization of Operation Pluto became a symbol of faith in the power of human intellect and spirit. And when it comes to the fate of this operation, perhaps its success or failure depended not only on technical details or strategic plans, but also on the outcome of the entire war on the Western Front, the destiny of millions, the future of peace, which still hung in the air like an invisible but very real challenge. And so, when dawn painted the sky in gentle hues and the first rays of the sun touched the sea surface, something greater than just laying pipes was beginning. It was the dawn of a new era, the era when human genius and determination could overcome natural elements, military obstacles, and fears. Everyone understood that this risk, this bravery, and this belief in the impossible would change history. Because even in the darkest shadow of war, behind every success lay a powerful will to win, an invisible testament to the fact that humans are capable of more than they seem to believe. In the silence of the early morning sky, when the first sunlight barely touched the waves, an elusive, almost imperceptible battle of technologies was underway. In this conflict, little known to most, the fate of secret operations was being decided. Operations capable of changing the course of the war. Against the backdrop of raging seas and fog-shrouded shores, engineers and designers, like magicians, created the most complex engineering solutions to provide invisible support to the front. Their inventions, like invisible threads, stretched underwater, connecting shores and forming a new line of defense that could be the key to victory or defeat. It was a time when every mile, every connection, every meter of pipeline held strategic importance, and technological innovations became weapons, less visible, but no less powerful than guns or planes. At the heart of this secret struggle was the creation of specially designed pipelines, whose purpose was hidden. Their mission, to ensure long-term, reliable, and covert delivery of oil and resources. For this, two types of pipeline cables were used, each with its own features and purpose. The first, called highs, or essentially a cable with a lead core covered with paper insulation, reinforced with steel armor, and wrapped in durable jute with tar. This cable, like a combination of bone and muscle, was heavy and durable. Its weight exceeded 55 tons per nautical mile. It was created by engineers from Siemens Brothers and specialists from the Iraqi oil company, who, like alchemists, sought to combine strength and flexibility under wartime conditions. After all, this flexibility was essential for laying and subsequently operating pipelines at sea depths, where every second could be decisive. However, as is often the case in the world of technology, circumstances forced the search for alternatives. In this case, the shortage of lead, a strategic resource, led to the development of a second type of cable, hamel. It was made from solid steel, which made it more rigid and less flexible, but at the same time, more reliable and resistant to external influences. This cable became a response to the need for durability and safety under the constraints and dangers faced by engineers. They understood that each section of the pipeline had to be as resistant as possible to storms, corrosion, and potential enemy attacks. Therefore, despite the increased weight of the design, hamel was a crucial element of the system, capable of withstanding the test of time and the sea's fury. Connecting these sections was a task requiring precision and speed. Special screw connectors, so-called Conan drums, came to the rescue. These connectors represented a complex engineering solution, allowing long pipeline segments to be joined quickly and reliably. Their design ensured hermetic sealing and strength, as well as enabling installation even in challenging conditions, which was critically important given the need to minimize laying time and eliminate errors. In wartime, such technological flexibility could be decisive, as every hour could determine the success of the entire operation. The production of these unique cables and connectors was carried out at two main centers, in the United Kingdom and the United States. There, under wartime conditions, engineers upgraded existing vessels and built special platforms for laying pipes. These platforms were complex structures capable of supporting heavy equipment and ensuring precise placement of pipelines at sea depth. In these workshops, where the sounds of welding and the hum of machinery merged into a continuous rhythm, technical masterpieces were born, capable of fulfilling tasks of any complexity. Time passed, and testing new solutions became the next stage. By early 1942, when the war reached its peak, engineers began testing their developments. They conducted these tests in the Medway River, chosen for its similarity to the seabed, and in the Clyde Strait, where conditions closely resembled real underwater laying scenarios. There, amid the noise of water and the clatter of mechanisms, prototypes were tested, their strength, hermeticity, and resistance to external influences verified. These tests were not only technical but also psychological. Engineers understood that the fate of millions depended on their decisions, on their precision and reliability. They saw how the tests confirmed the reliability of their solutions, how the evidence was irrefutable. Their cables and connectors worked exactly as intended. By October 1942, after numerous successful tests, a total of 10 30-mile sections of pipeline had been prepared, which were to become the arteries of naval support for the war. Readiness for sea trials and laying meant that the operation could begin at any moment. At that time, it seemed that all efforts and knowledge were concentrated on one goal: creating a system capable of providing continuous support to the front, invisible but vital. However, the main question remained unanswered. Could these technological solutions withstand the pressure of time, the dangers of enemy attacks, and the challenges of the sea. Could they ensure the durability, safety, and stealth of the pipeline installation? This question hung in the air like a heavy shadow over the entire operation. After all, the success or failure depended not only on strategic advantages, but also on the fates of thousands of people living and dying in the conflict zone. Those waiting at the other end of the line, hoping for the reliability of these invisible arteries. And it is precisely in this question that the great secret of technological victory lies. A victory that could become the key to strategic advantage, providing long-term support to the front, creating an invisible line of defense capable of withstanding the test of time and the sea's fury. This victory was not achieved solely through weapons or numbers. It lay in the genius of engineers, the precision of calculations, and unwavering faith in technology. And it was this faith that could determine the outcome of the entire war, becoming the invisible force that would push fate toward a final decision, victory or defeat. In June 1944, during the height of the Allied landing on the French coast, something greater than a mere military operation began. It was the start of a large-scale, incredibly complex, and ambitious project, laying pipelines designed to supply the front with fuel and resources. The times were difficult. Weather, sea clashes, dangers, and technical difficulties became constant companions for those daring enough to undertake this task. It was on this day, when everything seemed driven by intuition and hope, that the first stages of this aquatic engineering battle were laid. The initial lines, stretched across the sea surface, faced invisible enemies, storms, collisions with ships, accidental damages. The water, which was meant to become the bloodstream of the front, turned into a battlefield where each damage could be decisive for the entire operation. These first installations were not just technical tasks. They were a manifestation of determination, faith in technological progress, and strategic thinking. Just recall how, on one of the hot August days, on the 14th of the month, despite a ship accidentally snagging one of the pipelines, engineers and workers managed to complete the connection between White Island and Kerbosh. This node became a symbol of the first victory, proof that even in conditions of chaos and unpredictable obstacles, human ingenuity is capable of finding a way out. The pipeline was laid, connecting two important strategic points, albeit with some damage, but it was there, on the water's surface, like a living thread that could become a vital artery of the front. Months passed, and the construction continued. During this time, new tasks and challenges arose. Certain sections of the pipelines, which later entered history under names like Hayes and Hamel, faced difficulties that hindered their full operation. Initially, it was assumed that these lines would form a reliable network capable of supplying the front with fuel and resources in the volume necessary to sustain the offensive. But reality proved to be harsh. Not all sections could become fully functional. Technical failures, damages caused by storms, collisions, as well as errors in calculations and design, all turned hopes into disappointments. However, despite setbacks, the team of engineers and workers did not give up. In September 1944, the first full operation of the pipeline, named Hayes, was completed, delivering fuel to the port of Kerbosh. This fact marked a major victory, demonstrating that despite all difficulties, the project was moving forward. But these victories were fragile. The evidence is undeniable. Many lines suffered damage and could not provide the expected throughput. War is not only frontline battles, guns, and infantry. War is also engineering, logistics, and a constant struggle against nature, against time, and against one's own limitations. By October 1944, most pipeline lines had failed. Overestimating pump capacities, technical errors caused by haste and oversights, all of this led to the system, which was relied upon, becoming practically inaccessible. Sometimes it seemed that this complex network was like a fragile crystal, which any storm or miscalculation could shatter in an instant. And this destruction was not only material, it undermined morale, trust, and strategic plans. So an important question arises. Was all of this, laying pipelines and operating them under wartime conditions, truly strategically justified? Or were all efforts in vain, given that technical and logistical difficulties, as well as unpredictable natural factors, nullified all achievements? What was the value of this large-scale project? Were its results truly significant for the overall course of the war? Or did they merely show temporary successes that could easily be destroyed under the pressure of unforeseen circumstances? This question is not just rhetoric or a dilemma. It is the very essence of the picture of war, where every victory and every defeat are woven into the complex fabric of strategic thinking. Each line, each layout is not only an engineering solution, it is a bet placed on the future. Even in cases where everything seemed lost, when lines were destroyed and equipment failed, there is a profound lesson to be learned. A lesson that, even in the darkest and most hopeless situations, the experience and technology gained during this grand project will not be wasted. They will become the foundation for future strategies, new engineering solutions, and an understanding that humans are capable of overcoming invisible boundaries of possibility. Despite all setbacks, this experience has become a crucial stepping stone that, in the future, could be the key to more efficient, reliable, and well-thought-out systems. This is the essence not only of this project, but of all military progress. Every mistake, every damaged line, every technical misunderstanding is not just a defeat, but a valuable lesson that over time transforms into new knowledge and new opportunities. And at the very last moment, when it seems everything is lost, this experience, like an invisible thread, connects the past and the future, proving that even from the ashes of failure, something new, strong, and vital for all humanity can be reborn. When the Allies landed on the French coast, a new chapter in the history of military operations began, bringing not only heroic battles and strategic maneuvers, but also the most complex logistical puzzle. In conditions where the front was expanding, and the fight for every mile of land turned into a deadly race, one of the most critical issues was fuel supply, fuel without which the engines of mechanized power, aviation, and ships simply could not operate. In this context, behind heroic assaults and strategic plans, a unique and simultaneously mysterious initiative emerged: Operation Pluto, a mission that was to become not only a technological achievement, but also a key element in ensuring the success of the entire Allied offensive campaign. After the Normandy landings, despite the partial failures of the first days, the situation on the front began to change thanks to the efforts, mobilization, and courage of thousands of soldiers. However, the importance of fuel supplies, especially in the initial months, remained critical. In areas where fighting was particularly fierce, such as Port-en-Bessin and Cherbourg, the instability of maritime delivery became a source of constant tension. In these ports, where Atlantic waves crashed against the docks and weather could halt supplies completely within hours, it seemed that reliable logistics was a myth. It was here, under the pressure of necessity, that the idea was implemented, which later received the name Operation Pluto, oil field. Initially, the idea seemed risky and even reckless. Create a pipeline system capable of stretching across enemy territory, overcoming obstacles, enduring the pressure of time and combat conditions. This was a challenge for engineers, designers, and the entire engineering thought of that era. But it was precisely in these challenges that hope lay. From August, the month of resurrection after the landing, until May of the victorious conclusion of the war, about 780,000 cubic meters of fuel were transported through the pipelines. This figure, which seems insignificant compared to the overall supplies of the Allies, in reality became an important part of the overall supply system. It accounted for approximately 8% of the total volume, not enough to consider it the main supply, but sufficient to reduce dependence on vulnerable sea transports. The first months after the landing showed that despite the technical complexity and the need for numerous inspections and repairs, the pipelines could not fully replace maritime shipments. In the early stages of the operation, most of the fuel was still delivered by ships, in barrels and tanks, which seemed to cry out about their vulnerability, targets for German submarines and torpedoes, and susceptible to storms and delays. However, with each month, as infrastructure was established and technology improved, the role of the pipelines became more and more prominent. By January 1945, the daily volume of fuel transmitted through these systems reached 35 tons. This was only the beginning, just a start. By May, when victory already seemed almost achieved, the volume reached 4,000 tons per day. Such growth was not merely a technical achievement. It became a symbol of the drive for independence, for creating a resilient supply system capable of functioning regardless of sea conditions and enemy incursions. This engineering adventure had not only practical significance, but also strategic importance. In a situation where German submarine warfare and air raids made maritime routes dangerous and unpredictable, pipelines became a kind of insurance, a guarantee that even on the hardest days, the front would not be left without fuel. They reduced dependence on vulnerable transport means, allowing the front to receive energy without delays and with fewer risks. It is no wonder that by the end of the war, when the situation began to stabilize and ports expanded, the role of the pipelines diminished. But to completely abandon them was impossible. They remained part of a system that provided strategic flexibility and reliability. When the war drew to a close and the Allies began consolidating their positions, the Operation Pluto system, like a tired but resilient branch of a tree, was dismantled. In August 1945, immediately after Germany's surrender, the process of disassembly and disposal began. Components that were still preserved were sold or resold, their role in history having come to an end. But despite this final page, the story of Operation Pluto was not forgotten. It became an example of engineering brilliance, demonstrating how humans can overcome technical and logistical obstacles to achieve victory. Yet the main question that remains a subject of debate and research to this day is, how justified and effective was the investment in this operation? What was its true contribution to the victory? Was it merely a technical experiment or a strategic necessity capable of changing the course of the war? Answering these questions requires not only analyzing the facts, but also understanding that in war, success depends not only on weapons and tactics, but also on the capabilities of logistics, engineering ingenuity, and strategic planning. Despite its limited direct impact, Operation Pluto proved not only the technological possibilities of its time, it demonstrated that even in the most difficult conditions, humans are capable of devising solutions that can become key to the success of an entire operation. It became a symbol of how engineering art and strategic foresight can work hand in hand, creating unpredictable advantages. And in this lies its true value and lesson for future generations. Even the smallest and seemingly unnoticed details can be decisive in the most fateful struggles. Amidst the chaos of World War II, among raging battles and destroyed cities, one of the most ambitious engineering operations of its time was born. Operation Pluto. Named after its original abbreviation, Pipeline Under the Ocean, this project was not just another military endeavor, but a true test of human ingenuity, technological daring, and strategic thinking. Its final results, evaluations by historians and modern experts, form a complex kaleidoscope of opinions, testimonies, and legacy that deserves deep analysis and reflection. During its operation, despite numerous difficulties and limitations, the pipelines laid on the seabed of the English Channel delivered approximately 18 million gallons of oil. This number is not merely statistics, but a testament to how powerful and technologically advanced this solution was. Imagine thousands of kilometers of underwater pipes laid in conditions where the technologies of that era were only beginning to explore the depths of the sea. All achieved through innovative methods, bold engineering solutions, and the perseverance of teams working under constant danger and limited resources. Operation Pluto was recognized as one of the greatest engineering achievements of wartime. Despite its complexity, it became a symbol of technological revolution, proof that even under strict wartime constraints, systems can be created that surpass expectations in complexity and scale. However, even the most remarkable achievements are accompanied not only by praise, but also by criticism. The leading experts analyzing this project decades later agree that despite some partial failures, Operation Pluto demonstrated the potential for rapid implementation of new technologies in wartime conditions. It was a kind of experiment confirming that even amid conflict, it is possible and necessary to seek new solutions and push the boundaries of what is possible. Historians such as Morrison and Poston emphasized the strategic importance and innovative nature of the operation. They noted that this project was not merely a technological adventure, but a crucial link in strategic planning, capable of altering the course of the war. These researchers saw Operation Pluto as an example of how scientific ideas, industrial craftsmanship, and military strategy could come together into a powerful force capable of overcoming any obstacle. However, not all assessments were equally favorable. Other historians, such as Peyton Smith and Morgan, expressed skepticism and highlighted that the contribution of Operation Pluto to combat operations was minimal. Evidence shows that only about 16% of the total fuel consumption was delivered via pipelines, which, from a strategic efficiency perspective, appears insignificant in the context of the entire war. These critics question whether the cost of creating such a complex system was justified. Was it a costly illusion that, despite engineering progress, failed to fully realize its potential in combat conditions? Despite these controversial evaluations, the memory of Operation Pluto has persisted. The remnants of pipelines lying on the seabed are not just relics of the past, but symbols of technological boldness and human determination. Some components still rest on the ocean floor, as a reminder that even the most ambitious plans can leave a noticeable mark. In the post-war years, Operation Pluto became more of a symbol of engineering courage, uniting science, industry, and military strategy. It served as an example of how technological ideas can inspire future generations of engineers, strategists, and scientists, even though its direct effectiveness in combat remains a subject of debate. Thus, a key question remains: can Operation Pluto be considered a successful example of engineering innovation, or does it remain in history as an expensive, underestimated, or even failed strategy? This dilemma does not have a clear answer. On one hand, achievements in underwater pipeline technology, the rapid adoption of new technologies, and the strategic concept of connecting the front and rear areas all point to a high degree of innovation. On the other hand, the actual combat results, minimal support for troops, and obvious shortcomings raise questions about its true effectiveness. Nevertheless, this contradictory balance between success and failure makes Operation Pluto a unique chapter in the history of military engineering. The results and assessments show that even an incomplete implementation of the plan left a significant legacy for future technologies and strategies. Even in cases where the dreams of extensive pipelines did not meet expectations, they still became a stepping stone for the development of new methods and approaches, expanded the boundaries of what was possible, and demonstrated that human creativity can overcome the most complex obstacles. That is why, despite controversial evaluations and ambiguous results, Operation Pluto remains in memory as a vivid example of engineering boldness, scientific inquiry, and strategic innovation. It teaches us that even the most ambitious projects, even those that did not achieve all their goals, can leave valuable lessons and serve as a bridge to future discoveries. And in this lies the true legacy of this operation, which, despite its limitations, has forever entered history as a testament to the capabilities and boundaries of human genius. Operation Pluto is more than just a military project. It is a striking example of how, in the context of global war, when every decision can be decisive, engineering skill and strategic thinking come together to change the course of history. At the heart of this large-scale endeavor are not only technical achievements, but also the spirit of human ingenuity, the will to win, and the ability to unite efforts of the state and the private sector toward a common goal. It is this ability, this synthesis of ideas and resources, that makes Operation Pluto truly a symbol of an era unparalleled in complexity and significance. Against the bleak realities of World War II, when every report of potential success or failure could be the last, Operation Pluto stood out as a bright testament to the fact that engineering creativity can become a weapon, powerful, unpredictable, and effective. The construction of underwater pipelines across the foggy English Channel was not just a technical challenge. It was a challenge to nature, to the enemy, and to oneself. In conditions where time was against them and resources were limited, the ability to quickly implement new technologies became the key to success. And although the project's results were relatively modest compared to the scale of the war, its significance was much deeper. It became a demonstration that even in the most difficult conditions, solutions can be found, and that even risky ideas, if properly executed, can shift the balance of power. The development of underwater pipeline systems inspired by Operation Pluto continued in the post-war years. Lessons learned from failures and successes formed the basis for future engineering solutions. The strategy embedded in this project was not only a matter of technology, but also a matter of mindset. The importance of preparation, planning, and the ability to innovate was evident at every stage of implementation. It was a lesson for both military and engineers. In wartime, not only the strength of weapons determines the outcome, but also the ability to think creatively, find unconventional solutions, and implement them swiftly. But most importantly, it is the realization that risk and ambition can matter, even when everything seems to be against you. Operation Pluto became an example of how military engineering can confront dangers without knowing exactly how things will turn out. And even if the project did not achieve all its goals, it left a legacy that continues to inspire today. Its heritage is not only in technical achievements, but also in the belief in the power of the human mind and solidarity, that even in the darkest times, there is room for hope and progress. In the modern world, where challenges evolve and the boundaries of possibility expand, the experience of Operation Pluto remains relevant. Today's engineers and strategists use it as an example, as proof that innovation and cooperation are the keys to success in any field, especially in times of crisis. The methods of fuel transportation and the development of communication systems in extreme situations are all part of the legacy of those days when the human spirit and engineering skill merged in the name of victory. Ultimately, Operation Pluto is more than just a technical project. It is a monument to engineering spirit, a testament that even the boldest ideas, even risky and complex ones, can become weapons in the fight for freedom. It proves that within each of us lies the potential for great deeds if we unite our efforts, believe in ourselves, and are not afraid to face the unknown. And this is the most valuable lesson of this story, a lesson that lives on to this day, reminding us that in any battle, success depends not only on the strength of the weapon, but also on the power of human intellect, unity, and determination.